So our next task is to do Chapter 6 on the uniform boundedness principle, or the Banach-Steinhaus theorem. So I think we're going to be focused on what I call the uniform boundedness principle. And then it has a corollary, which is also called Banach-Steinhaus. It's unfortunate there are two different results called Banach-Steinhaus, and it depends on who teaches the module, who calls which one which. But we'll be, the stronger of the two is called the uniform boundedness principle, and the other one is a corollary. So here's the uniform boundedness principle. It's again a result about Banach spaces, but this time only X has to be a Banach space and Y doesn't. There are actually some subtle variations. There are some varieties in this result as well, but this is the one that I'm going to call the uniform boundedness principle. And it's X that has to be complete for this one. That's the code, that's the domain where you're mapping from. And the idea is you've got a set of bounded operators. Maybe it could be an uncountable family. You've got a set or a collection of bounded operators from X to Y, and you want to know whether there's some uniform bound on the operator norm. So each one has got an operator norm, but the operator norms, of course, can vary. And of course, if you look, say you looked at all of the bounded operators between X and Y, then of course, although each one has got a finite operator norm, there's no bound on the operator norms, because particularly if you take any odd operator that's not zero and you scale it up, its norm's going to get very big. So you don't usually expect a collection of bounded operators to be a bounded collection of operators. Okay? So you don't normally expect to find a global bound on all the norms in your collection. But perhaps you can sometimes. Obviously, if you take a finite number of operators that are bounded, then you could just take the maximum of their operator norms, and it would be a bounded collection of operators with some global bound. But if you've got an infinite collection of bounded operators, then again you don't know. But perhaps you can put some condition on that does it. And of course, there's an immediate necessary condition that if your operators are bounded in operator norm, then it must be that for each point of the space you're working on, you get a bounded set of images, because they're going to be at most, everything's going to be at most a constant in norm times the original norm, this global constant bounding your operator norms. So you need what I call point-wise boundedness to have any chance. Point-wise boundedness means that for each point in X, it's this condition here, that for each point in X there should be some constant, so that for every operator in your family, the norm of the image is at most that constant. So this is not allowed to depend on T, but it is allowed at the moment to depend on X. You're going to need that if you're going to be bounded in an operator norm, because if you are bounded in an operator norm, then whatever that bound on the operator norms is, you can take that times norm X to be your MX. So you're going to need this. The uniform boundedness principle says that that's sufficient as well. If you're point-wise bounded as a collection of bounded operators on a Banach space X, then you're uniformly bounded. There's a global bound on the operator norms. And that's what it means. So that's what this says here. You've got a whole load of continuous linear operators defined on X, taking values in Y. Y can be normed. Doesn't matter, because you can always complete Y anyway. And then you'd be talking about maps into a Banach space. It's X that matters. Okay, then as long as they're point-wise bounded, that's this condition here. For each point X, we can find a constant that's allowed to depend on X, so that the norm of the image is at most of that constant that depends on X. For all T in your family, then there's some big constant, capital K, so that the norms of all the operators in your family are less than or equal to that big constant. So this is the point-wise bounded and this is uniformly bounded. At least this is the sense in which we're talking about uniformly bounded. So you have to understand what that means. That's the sense in which we're talking about uniform boundedness. In the usual sense of uniformly bounded, you can talk about being uniformly bounded on the unit ball, and then it will actually turn back into a completely standard notion of uniform boundedness. And we know that linear maps are determined by how they behave on the unit ball, so that's a perfectly reasonable way of thinking about it. Right. So the proof is another one of these symmetric convex sets about the origin bare category theorem arguments. So typical bare category theorem proof. Let me make sure I've got the notation in front of me. And we'll come back and do the corollary afterwards. So here's your proof of the uniform boundedness principle. That's proof of 6.1. I think this is slightly easier than the open mapping theorem. We'll set AN to be those x in X with the following property: that for all t in your family, we have the norm of Tx is less than to n. So notice that's a subset of X. Then you can check the following easily. We'll take this as obvious, but you can check it. AN is a closed subset of X and of course n is a natural number here. N is a closed subset of X and is convex. Things like this involving norm of Tx, it's quite easy to check that you'll end up with a convex set of X's. And symmetric about the origin, which is pretty obvious. If you replace X with minus X, you don't change the norm of Tx, so that bit's completely obvious. So it's already closed. We don't have to close it, which is nice. I claim that the union of these ANs is the whole of X. Well, to see this, we'll let X be an X. Then norm of T of X is at most mx, that constant that depends only on X, for all T in F. So for n in N with n greater or equal to mx, X is in AN. We use the point-wise boundedness. The family is point-wise bounded, so the set of images of X is bounded with norm most mx. So all you have to do is go far enough along your sequence of sets until you get to an n that's big enough that n is at least as big as mx, and then you're home. So we've got symmetric about the origin, convex, closed, and the union of a sequence of them being the whole of X. So what do we quote now? We will get that we will get that 0 is in the interior of some AN in a minute. But first we need to quote a theorem. Bayer category theorem. Okay? The most common form of the Bayer category theorem, if a union of a sequence of closed sets is a complete metric space, then at least one of those sets has non-empty interior. So by the Bayer category theorem, by BCT, there exists an n in the natural numbers such that the interior of AN is non-empty. But then, since AN is convex and symmetric about 0, it's symmetric about 0 and convex. We have that naught is in the interior of AN. So there exists an R greater than 0 with, and again we can take the closed ball, cent on 0, in X, radius R contained in AN. You can get an open ball in, so make it slightly smaller and you get the closed ball in. Then, for all X in that ball, we have, for all T in F, that norm of Tx is at most n. This particular n we've got here. Of course, I'm supposed to say something about the operator norm. So which ball should I be working with? This is the ball radius R. If I want to talk about operator norms, which X should I be considering? In which ball? When you're trying to find out what the operator norm of something is, what's the definition of the operator norm? Unit ball. We normally would use a unit ball. We want to know how big can the image be if you're working on the unit ball. So we've got to scale everything up. We'll scale by a factor 1 over R. So scaling by 1 over R for all X in the ball in X set at the naught radius 1, the closed unit ball, we have for all T in F that norm Tx is at most n over R. N, of course, was probably quite big because you probably had to go quite a long way. And R, well, as usual with the usual proviso, actually you can scale up and down using n and 1 over n, and you could have done something like that. R is probably quite small because you've got a small neighbourhood of the origin, so 1 over R is probably quite big, but it doesn't matter. You can just set capital K to be n over R. And then we see that for every T in F, the operator norm of T is at most capital K by above. For all T in your family, we have the operator norm of T is at most K. And we're finished. Any questions on that proof? It's a typical Bayer category theorem symmetric convex set proof. Okay, so we now have the corollary 6.2 Banach-Steinhaus. This is a nice fact about sequences of operators that converge pointwise. So it's an immediate corollary of the previous one. So you've got a Banach space, and you've got a norm space, and you've got a sequence of continuous linear operators from x to y, and it so happens that they converge pointwise to some other operator t. So they converge to something, but we don't know yet whether t is continuous. So they converge pointwise to some map t. Now it's very easy to see that t is linear. So just from the fact that these linear operators if a sequence of linear operators converges pointwise to another function, it's easy to show that thing is another linear map. So that's the linearity. The fact that t is linear is easy. It's the continuity that is interesting. That's an easy exercise. But actually, t is a continuous linear operator, and you can also prove that these tn's are bounded, and that the operator norm of t is less than equal to that bound. So why does that work? Well, because this sequence is convergent, that implies it's bounded. Every convergent sequence is bounded. So you can set mx to be the supremum of the modulus of tnx over n in the natural numbers, and that's finite. Because it's a convergent sequence, as n varies, the constant depends on x. But for each x, you get a convergent sequence, so it's a bounded sequence. And so you can, and this is a norm. Okay, and then you've got your mx, and then that means you can apply the uniform boundedness principle. The uniform boundedness principle shows that this supremum is finite. And then once you've got that, this other bit about the operator norm of t is dead easy. That's immediate because it's just the limit of these things, and you've got a global bound on how big those things can be. So that's an immediate consequence. But of course, the early TNs don't contribute because it's the limit of the TNs you're using. So it's only the later TNs that really matter. And so instead of using soup, you can use lim soup, which is the version of soup where you throw away the early terms and you only care about the late ones. So once you've got to soup and you realize it's about limits, you quite quickly get to lim soup as a consequence. But one thing that may surprise you is that what you don't get is that the TNs actually necessarily converge to TN norm. In fact, sometimes you can have some norm 1 operators, and the limit operator has got norm 0. In other words, they can so a sequence of norm 1 operators can converge pointwise to the 0 operator, and that's not difficult. But that doesn't violate this condition because 0 is less than or equal to 1. So you get an inequality one way round, but it can be strict. It can be that all the norms of the Tns are 1, but the limit operator is a 0 operator. No real problem in this setting. And you can think of examples of that. And that brings us to the end of the section on uniform boundedness. Any questions on the uniform boundedness section? Okay. So that means that all that remains is the material on commutative Banach algebras and the session on measure theory, which we're doing next week, and the optional revision session in May. And of course, for those of you who've got assessed coursework to do, and in G14 TAN, and also the oral presentation in May as well. But that's only for G14 TAN students, not for G14 Fun students.